Alright, hello everybody, and today I'm going to be starting a little introduction to integral calculus series on my channel right here. So I've already done a series on differential calculus, which is one part of calculus, so the differential side of things, and now we're going to be looking at the integral side of calculus. So let's just jump straight into it. What exactly is integral calculus trying to solve? Because differential calculus, we know we had a curve, and it was trying to solve the problem of what exactly is the gradient at a particular point on a curve. So something like that. So how about integral calculus? What problem is that trying to solve? Well, if we consider some curvy thing, like so, let's call this function f of x. Integral calculus is trying to find the area underneath a curve like so. And this is quite an interesting problem because this is actually very difficult to do because we know how to calculate the areas of squares, rectangles, circles, triangles, maybe ellipses if you've learned how to do that. But an area under any function is actually a lot more difficult to do because you can't really fit squares or circles or triangles inside of this to somehow kind of break it up or something. We have to use a much more different approach. And the way to do that, I won't go into too much of the mathematics in this video. If we consider some, I don't know, let's say some cubic function for now, nice little cubic. If I want to find the area from point A all the way up to point B, the way we do that is we actually want to approximate the area a little bit first. Just like with differential calculus where we add a curve and we can estimate the gradient at a particular point by using two separate points. In integral calculus, to approximate the area right here, the area of this region, what we actually do is we actually break it up into much more simpler shapes that we know how to calculate the areas of, namely the rectangle. So if we have a rectangle, formula to find its area is just base times height. And that gives you the area. So what we're going to be doing with this area right here is we're going to be approximating it using nice little rectangles that fit nicely underneath the curve. And while you might be saying, well, that's a pretty bad approximation, but the thing is, the smaller we make these rectangles right here, the better our approximation will be. And here I've just drawn up 5 rectangles, so it is a pretty bad approximation, but it's an approximation that will get better and better the more rectangles we have. Just like with differential calculus, the gradient of our secant right here will be a better and better approximation of the actual tangent gradient, the smaller we make this little gap right here. So I'm just going to touch on a little bit of mathematics in this video. Let's actually try and find an expression for the approximate area of this curve using all these rectangles right here. So when we do this, we actually let the width of each of these rectangles be some small change in x, and we call it delta x. So each of these will have a width of delta x. And then notice that we're kind of dealing with multiple x values right here. So we're going to give each of those x values a name. Let's call them x1, x2, x3, x4, and x5. And well, if we know these x values right here, then we can easily find the corresponding height of each of these rectangles right here. If this is y equals f of x like so, the height is just a y value, which is just plugging each of these x values into this function. So the height will have f of x1, f of x2, and so on. So we know the height and the width of each of these rectangles, and now all we have to do is sum all of them up. So we're going to have f of x1, so we're dealing with this first rectangle first, so we have the height, which is f of x1 times the width, delta x, and this right here will give us the area of one small little rectangle. And then we're going to be adding them up with all the other ones, f of x2 delta x plus f of x3 delta x, and so on. And all of these rectangles right here, when we add them up, it's going to give us the total area of the curve. But just to be clear right here, this right here is just an approximation of the area, but it's an approximation that will get better and better the more rectangles we have and the smaller we make each of these delta x's right here. So we want our delta x to be small, as small as possible, and the smaller it is, the more accurate our area will be. So that is kind of the general idea of integral calculus. To find the area underneath a function or a curve like so, we're just breaking it up into small rectangles. And the reason for doing so is, well, we know how to work with the areas of rectangles. They're really easy to calculate. And just like with differential calculus, I'll emphasize this one more time. This is an approximation that will get better and better the smaller we make these delta x's right here and the more rectangles we have. So that is pretty much it for the first video in this series. Just a little introduction, and in the next videos we're going to be diving a bit more deeper into the heart of integral calculus. But until next time, have a wonderful day, and I'll see everyone later.